Cool.
And yeah, I'll just hand it over to Ben to introduce the paper and everything. So go for it, Ben.
Okay, thanks, Peter. Hi, everyone. Thanks for having me to Paper Club. So the paper we'll be reading today is called Score-Based Generative Modeling through Stochastic Differential Equations. So I just want to check you can see my screen. You can see the PDF. Give us a nod, Peter. Cool. Nice one. So this paper is authored by Yang Song and co-authors. But first of all, before I get into the paper, as Peter was saying, you can jump in with a discussion point, put something on the chat, and I'd really want to encourage everyone to jump in with questions, but also discussion. And if we can make this as much of a discussion as you'd like, then that's good for everyone, I think. So yeah, feel free to jump in at any point and put questions in the chat. So going into the paper, I think it's useful to begin with just to break down what the title is saying. So score-based generative modeling through stochastic differential equations. What is score-based? So if we go to another paper, right here, I think authored by some of the same authors right here. So improved techniques for training score-based generative models, Yang Song. We have a nice description of what the score is. So for any continuously differentiable probability density P, we can call nabla x log probability of x its score function. So here's the density of some, let's call it a vector x, some states, which could be high dimensional. This could be a single sample of an image, one realization of P of x. So we want to sample from a high dimensional distribution. And then the log density is called a potential. And then the gradient of the potential with respect to the state x is its score function. Now, in many situations, the score function is easier to model and estimate than the original probability distribution, not least because P of x requires knowledge. Evaluating P of x requires knowing something called the partition function, which is the normalizing constant of this distribution, because distributions must sum to 1. That's what defines them. But usually this partition function is a high dimensional intractable integral. So we want to avoid having to evaluate the probability density exactly. And so in two situations, using the score function directly allows us to do two different things. One of them in generative modeling is sampling from this distribution. So going from noise to data, that's generative modeling. And the other one is using this score to estimate P of x. And so those are two tools that we have when we want to summarize a data set from the real world with a model. We can call that model a probability distribution. And then once we've summarized the data set from the real world with a probability distribution, then we can do things like sample from it. That's generating new images. We can do conditional sampling, which is an inverse problem. Inverse problem is just the application of Bayes' rule. And so then we can condition on text to generate images. You might have seen that being done. We could also do things like have a physical model encoded in the probability distribution and condition on sensor data and boundary conditions to sample to simulate physics. We could quantify quantities of interest, such as risk estimates that depend on a model. We could do inference, which is another inverse problem, which is inferring what the parameters are of a model from observed data. So this is quite a general framework, generative model. So typically, once we have a score function, and we can evaluate this, then we can usually sample from P of X. And one way of doing that is by using Markov chain Monte Carlo methods or score-based Markov chain Monte Carlo methods. And one of those is called Laundromat Dynamics. This is Laundromat Dynamics. So it's actually doing the same thing as generative modeling. It's going from noise on the right-hand side to data on the left-hand side. But there are a few problems with directly applying Laundromat Dynamics. So I can.
So sorry, when you say it applies, but it just applies noise, right? But there's still data on the right-hand side as well in the x t-1.
Yeah, exactly. So this is an iterative algorithm.
Yeah.
It's sampling from a stochastic process whose dynamics are described by the score function.
Yeah.
And so I can illustrate what the score function looks like.
So there's like a drift and the diffusion. Yeah.
Yeah. So if I estimated, actually, I can directly calculate the score function of this data distribution. You can see this distribution right here. Hopefully you can see the image of the circle. Yeah, so these are samples from the unit circle in X, where X is two-dimensional. There's two axes, right? So this is clearly not an image, because an image is 64 by 64 dimensions. That's way more dimensions, or even 1024 by 1024 dimensions. This is just two-dimensional. And the distribution lies on the unit surface of this circle. And if I can sample from that distribution, then I can calculate a score from the empirical data distribution. And that score looks something like this. And Laundromat Dynamics, what it's doing is it's sampling from a prior distribution and then moving in the direction of the dynamics. So you can think of it like a gradient descent, but with added noise. Okay, so it's like an optimization algorithm with noise. And so if I go through the Laundromat Dynamics, this is an example of what a sample trajectory might look like. And hopefully in a finite number of function evaluations of the score, this vector field right here, I've moved to an area of the state, which is a sample, an approximate sample from the density P of X, which is on the unit circle. But there is a number of problems with just using the score to go from noise sample from the prior and adding noise at each step and going in the direction of the score to get a sample. And one of those, I mean, there's three that I could think of. One of them is that when I'm going through these dynamics, I can move quite quickly in one direction. But once I get to this potential well here, it takes a very long time to move slowly around the edge of the circle. So if I want to explore the whole distribution, then it's going to take a long period of time, just because the dynamics in one direction are very quick, and the dynamics in the other direction around the edge of the circle are very slow. And that's called mixing. And this mixing problem is especially a problem when you have score functions that are non-convex. And a convex function looks something like this. And so if you could see, this is in one dimension now, the Laundromat Dynamics would sample from this potential well, but I'd have an issue if there was two wells, I'd have an issue moving to the second potential well, and that's called poor mixing.
When you showed the ring there earlier, right? So it would in principle have no problem getting around the ring, right? It would just be relatively slow because it's just purely diffusion that would push it along the ring. But because it doesn't really have to go over a potential barrier. It will happen with a high chance. Whereas if you had another, as you say, maximum somewhere else, a minimum somewhere else, then potentially would be hindered to ever go there.
Yeah, I think it will explore the space eventually, the space of the support of the distribution. It will just take a long time. It's got a large fixing time.
Yeah, but potentially infinite, right? So it's
it depends on the convexity or non-convexity of the particular score function.
It's actually I don't know the mathematics enough. Is there, if this vector field is truly a smooth vector field, convexity is almost bound to happen, right? So this vector field itself must be somewhat strange, if I remember.
So convexity is limited to potentials that look like this, and so this is only a unimodal distribution. So as soon as it's multimodal, it becomes non-convex. So it's actually extremely common to see non-convex distributions that you want to sample from, and it's the only thing that can happen when you have a limited amount of data. So if I now have a smaller amount of data on the ring, and then I evaluate exactly the score function, the score function is going to be not accurate in regions where I haven't sampled from. So between the data points here, the score function is not accurate. And so when the Laundromat state, the sampler, goes into these regions, then the samples won't converge to the correct distribution. And score-based generative modeling is about using SDEs to remedy that situation. So it essentially smooths out these potential wells with added noise. And what that translates to, after you go through the maths, is what you're trying to do is essentially predict the added noise to your data. So I sample from this distribution, I add some noise, and then I use a neural network to predict the score, which is just how much and in which direction I've moved this sample. So you can see the score is pointing in the direction of the data distribution. If I take the data and then add some noise, the score will be the direction and then the magnitude of that noise. So that's why it's like predicting how much added noise you've added to the data. And the more noise you add, the more it smooths out this potential, and the nicer properties it has, and the easier it is to explore the whole space. So that's one way that we're getting around the poor mixing of Laundromat dynamics when you have non-convex potential. There are two other, I think, difficulties with sampling, and they come from a dimensional dependence. So when you don't have 2 dimensions, but you're dealing with images, you have many dimensions, possibly infinite dimensions, then the number of score evaluations it takes to get an approximate sample from this distribution scales with that dimension. So if you imagine an image is 1,000 by 1,000, that's 1,000,000 dimensions, then it would take, in the worst case, millions of evaluations of the score to get a true sample from, or an approximately true sample from the distribution of the images of faces, let's say, which would just take too long. The algorithm may involve a filtering step as well to correct a bias that's introduced by a discretization of this sample trajectory. So because you can't sample continuously, you've got to discretize to get into an algorithm that you can compute. And that step could even be undefined in large dimensions. So when there's not enough data and we want to explore the whole space, then we can use SDEs to kind of temper this distribution and sample from it more easily. So that is essentially what we use the SDE for. Are there any kind of questions or thoughts at this point? Okay, Toby's got a question.
Yeah, so you compared it to gradient descent, which is sort of, let's say you want to find a minimum. But here, if you're sampling, surely you don't always want, let's say, the most likely value of X. You'd want to sort of like sample from, you'd want to sample from there the most, but you'd also want different samples, whereas it sounds like you're always going to get the most likely sample here, if that makes sense.
Yeah, so it's not gradient ascent, it's noisy gradient ascent.
Yeah.
Okay, so the target density of this Markov chain is the distribution P of X.
Right. Okay.
So that's coming from adding this noise here.
I have a question. So before you mentioned that if we just learned the score function from the data, we would learn like an overly exact, or not exact, maybe like basically the potential field would just push you to the points that are in your data set as opposed to like the underlying distribution. And that what these methods that we're going to be looking at are trying to do is actually learn the noise that is used to sample from the distribution or something along those lines. But I was thinking to myself, if you only have the samples in your data set, don't you have to use make an assumption about the sampling noise? Or essentially like you can't really learn it from the data. You have to make an assumption somehow with like an inductive bias within the model. So to go from like from the dots that you showed to the circle that you showed before, you probably can't learn from the data that it should be a circle, but you have to make some kind of prior assumption or in order to get to the circle.
Yeah. Isn't the alpha to some extent a free parameter, which to one extent it actually tells you how likely it is you can jump out of any given minimum, right? So if your alpha is significantly higher than the integral over the gradient of the equilibrium distribution, then you're quite likely to be able to jump in between different minima. At the same time, if you make it close to zero, then essentially it becomes completely directional, right? So then of course you can argue what does the gradient then mean, but yeah, it's technically you could have an alpha that's arbitrarily small, right? If the equilibrium distribution is a gradient is still well defined. It's just or sufficiently wide, I would think.
Yeah, so I think there's two questions here. So Arvid's question, what value of alpha to choose? So essentially it's as small as possible, because when alpha is sufficiently small and T is sufficiently large, i.e. like the smaller alpha is, the less discretization error in the discretized Laundromat dynamics. Okay. So yeah, I think this is a discretized algorithm. This isn't a continuous time stochastic process. This is an iterative algorithm that depends on the step size alpha, and the step size alpha, decreasing that will decrease the numerical error in this. And that's important because you want to sample from the stationary distribution P of X. And if you make alpha too large, then you're not going to be doing that. But there is some kind of a trade-off. You want it to be sufficiently small enough to sample from P of X. But if you make it too small, then you're not going to explore the space. You want it large enough to explore the space. And also so that you don't need to have as many evaluations of this, because the smaller this is, the more evaluations of this you need to converge to P of X. And I think it's a good question, but it doesn't. I don't think alpha is to do with like bridging the gap between a finite empirical distribution of data to like sampling from a true distribution. Basically, Peter, I think we'd never ever have access to the oracle, like the true circle distribution. We can only approximate it through data. And so we do need a lot of data to sample from all of the support of that circle so that the score is accurate to an arbitrary small number. But there is inductive biases as well coming into play. For example, the score function is parameterized by a neural network. The reason we parameterize the score function by a neural network, even though we can compute it exactly from the empirical distribution, is because this right-hand side, nabla x log p of x, involves a sum, and it would be too costly to evaluate that sum every time step, this algorithm. So we approximate it with the neural network by score matching, and so we can evaluate it like that and just take samples. But that involves an approximation, and that approximation will induce, would constrict you to a space of functions. Let's see if this has anything about that. So yeah, so they've notated that here by saying that S must be in this space of functions, which is the parameterized neural network, and we can put different assumptions on what that function looks like. For example, if I made S a matrix that you multiply by X, then you only sample from Gaussian multivariate distributions. And so you do have an inductive bias, and that might be able to help with generalization. There might be something that means that you need less data if you're approximating the score because of an inductive bias that you've put on the neural network. But in general, you'd need just a lot of data to be able to approximate the exact log density to a good degree.
Thanks.
Okay, so I think we talked about like the underlying maths for a bit. We could look at what it's doing when you scale up to large dimensions. So this is the forward SDE that's adding noise to the data, and then score matching is approximating this, so you don't need to evaluate it exactly by parameterizing a neural network and then matching the score by predicting how much noise and in what direction the noise was added. And so the simplest SDE that you can use to add noise is an SDE that adds Gaussian noise and would converge to a stationary distribution that is IID normal distribution. So this is Gaussian noise. And then once you've used this to add noise to temper the distribution and approximate the score function at each step of adding the noise, then we can reverse that process by subtracting noise. And that's what the reverse SDE does. So this is a step beyond Laundromat Dynamics. We've now got annealed Laundromat Dynamics.
I actually had a question about something you just talked about when Naif was presenting his work, which is, you said that the image was like IID Gaussian noise, but is it the image or the pixel values? Like, is each pixel independently distributed Gaussian noise, or is it the image as a whole?
Each pixel, yeah. So each pixel is a dimension. Each pixel is an axis on the, the circle plot. Each pixel will have its own axis. So you can imagine there's here in this image, it looks like 60, 64, maybe 128 pixels. And then you multiply that by 128. So you've got 128 multiplied by 128 dimensions, multiplied by 3, because it looks like an RGB image. So those are, you need 128 times 128 times 3 numbers to describe an image in this case. And so that means, yeah.
Because the main question, and this was something, was, so if you just randomly if say you have two classes in your data set, like cats and dogs, and you train them, like you train which is like in a simple way, probably like a bimodal distribution. And you train them, you learn a score function, and then you start with the image on the right. How would you go from that to dog versus cat? Like, what would be the differentiation in the like the Gaussian noise distribution if each pixel is like Gaussian noise?
So that sampling from the prior at that point, when you're sampling from this Gaussian noise, where each pixel has 3 numbers, which are the colors, which are all normal 0, 1 Gaussian noise, then there is no differentiation at that point. The differentiation comes when from the noise, from the perfectly annealed or tempered score function, emerges a score function that has 2 modes. That's this like non-convex shape with 2 bumps, one for cats, one for dogs. And eventually, you can see it in this example right here, that from sampling from this unimodal distribution, which is prior, in the reverse SDE, eventually by chance, you will be one side of the bimodal distribution. And because then the score is non-convex, you're going to stay there because you can't jump this potential barrier. So eventually, by chance, you will be sampling from a cat or sampling from a dog. But this is like a really important point because it points out a disadvantage of score-based modeling. Because the score is a derivative of the density, it only includes the local information about what the score is. So that means that it's when the density is small, here 0, this is actually the most important point for telling you how many cats there are and how many dogs there are, like the score at this point between the 2 distributions, because the score at this point determines the height, the relative height of these modes. But because the density is 0 here, it affects, what it leads to is that it's very difficult to correctly estimate the score in this region, and therefore it's difficult to correctly evaluate the relative height of these modes. So if you had a data distribution that was cats and dogs, then you might find that when you started sampling from this distribution, you'd get relatively different numbers of cats and dogs compared to the data you used to generate it. So that's actually one limitation.
Thanks.
So before we go back into SDEs, because this was a continuous process, there's always a simpler way to look at it in terms of its discrete process. And those were the previous attempts. So one is called denoising score matching with Laundromat Dynamics. And the other one is called denoising diffusion probabilistic models. And they both aim to do approximately the same thing. It's like the Laundromat Dynamics, but you add noise progressively at each step and then reverse that process to sample from a distribution and at the same time explore the whole space. So, and also kind of remedy the fact that you don't actually have a lot of data. So at each step I, you have a Laundromat Dynamics where there's m steps, m function evaluations of the score, which you approximate with the network. But then you sample big M times the Laundromat Dynamics at each noise step. So then there's an outer loop. There's the inner loop over M, the Laundromat Dynamics, and then the outer loop over the noise that you add. So at each step, you increasingly add more noise so that eventually the distribution at time step big T is sampled from the prior. And then the reverse of that is sampling from the data distribution at I is 0, at T equals 0. And so there's a discrete number of I steps. There's n I steps. So there's n points, n layers at which you add noise to the data distribution. And what this objective is doing is it's predicting the amount of noise. So this log density is a conditional one. And because the kernel is this, so this is a conditional distribution, then when you evaluate it, you find the log density is actually just a 0, 1 random variable, because it's like x tilde minus x over sigma, which is just the z-score, or like a normal 0, 1 random variable. So this turns out to be noise scaled by sigma I. And so then you can multiply up by sigma I and learn a neural network, which is the predicted noise added to your distribution. And that's how you extract the information from the image. And largely this method is doing more or less the same thing. It's got the same objective function. It's got the same terms in the objective function. And it's also sampling from a Markov chain, which is not quite Laundromat Dynamics, but it's something quite close, because you've got the board here and you've got the added noise at each step here.
I have a question. Is equation 2 just the Euler-Maruyama method for the Laundromat stochastic ODE?
It is, yeah.
Okay.
So here you've got alpha in the previous paper we looked at. It's now beta, but you have to predefine n steps, and so that's just like discretizing the continuous process with the Euler-Maruyama discretization. So yeah, but the choice, the design choice involved is picking the sigma I at each step, the added noise. But when you have an SDE, you can work out math such that this is prescribed by the method, that you don't need to parameterize this method by an annealing schedule, which determines the sigma I. And the way that is done is by, as you see in a lot of papers these days, it's generalizing a discrete version of an algorithm to a continuous version of an algorithm, working on the maths in that continuous space, and then translating what you've learned to an algorithm when you discretize again. So instead of adding discrete steps of noise, you've now got the difference in the state, the sample, is the drift applied to that sample plus some noise. But this noise is a Brownian motion, so it's continuous in time. And then this essentially means that you've got a very large number of steps that you're adding noise, and the sample trajectories will look something like this. So I don't think there's much else I want to say about the SDE, other than it's generalizing those two approaches here. And it's through the generalization that you end up getting state-of-the-art performance on the examples, such as conditional image generation.
I have a quick question about sort of the SDE picture before, about the transition picture. Is it impossible to have transitions between the two modes on sort of the right-hand side of the right picture? Or is this sort of are transitions impossible up to like from a certain point onwards? Or
eyeballing it, I would say transitions are probably impossible from around this point in time, right? I mean, just looking at the image. But question is,
yeah,
how to analyze that.
Yeah, because I could see transitions happening like far into the picture, like they would just be really rare, right? But then, or like completely on the far right, it looks impossible. But, yeah, no idea.
Yeah, I mean, the mixing at this point is very poor because you can't jump between the modes, but the mixing at this point is better. And that's one of the reasons why this method works, because you can explore the whole space of the distribution here when you've got an annealed score. But progressively, you get closer and closer by subtracting the added noise to a sample from the true distribution, which in this case is bivariate Gaussian. Sorry, not bivariate Gaussian, multimodal, bimodal Gaussian. Yeah. But yeah, at some point, the mixing becomes poor, but you don't care because you're already sampling from the whole space early on. Is my interpretation of why an SDE would be used. And so you can think the more you refine this time axis, the more you'll be able to explore the space so that you can eventually converge on the prior distribution, because there's kind of three sources of error in score-based generative modeling. One of them is how well you approximate the score with a neural network. Another one is how well you discretize the SDE, so how many time steps you use. And the third one is you don't actually sample from PT of X when you generate a new image. The idea is that if you add enough noise, eventually it will look close enough to a normal 0-1 distribution over lots of different dimensions. But that's not actually what is not actually converged at this point to a normal 0-1. It's just something that's close to that. So that's another approximation that's used, is when you actually generate images and simulate through the reverse SDE to go from noise to data, then you are sampling from a prior, which is you're saying it's close enough to a 0-1 distribution. So the idea is that if you use an SDE instead of a discrete number of time steps, annealing schedule, as is done in the denoising score matching, then you can analyze how many time steps you need to reduce the discretization error. You can analyze what kind of neural network you might need to approximate the score function to an arbitrary accuracy. And you can say how long you need to simulate the forward SDE for to sample close enough to a normal 0-1 distribution. So it's by like posing things in this continuous framework that you can do analysis in order to get bounds on sampling. And so you can say, I need n time steps, I need this neural network, and I need to sample for this amount of time. Yeah, so it's kind of like getting the method from doing analysis with these SDEs. Okay, so there's one other thing that is going wrong so far, in that you can't just simulate this reverse SDE because at each step, nabla log P of X is changing because it depends on the time. It depends on the amount of noise that was added because it gets sharper and sharper and sharper to the true image. And so you need not only the predictor, which is sampling from the image, but a corrector to say that at each step, you're sampling from the true distribution PT of X. So that's what the corrector is doing. So let's go down to this section of the paper. Predictor corrector samplers. So yeah, unlike the Laundromat Dynamics, the Laundromat MCMC, so we don't just have a single nabla X log P of X. We have a large number of these in that we have them for each time step. But we need to make sure that at every time step, we get close to converging to the true PT of X distribution. So at each time step, the numerical SD solver first gives an estimate of the sample at the next time step. So that's going forward in time by denoising. and that plays the role of the predictor. Then the score-based MCMC approach corrects the marginal distribution, which is the sample PT of X, of the estimated sample, playing the role of the corrector. So it's making sure that after sampling this Ornstein-Uhlenbeck SDE, the dynamics are moving quite quickly, but you want to kind of pause each time step, make sure you're in the correct area of the distribution, and then go again. So that's correcting any step, and it's basically correcting a bias that's induced by a numerical error in the solution of this SDE. And so it means that you don't need to do as many function evaluations. And because we always have a finite compute budget when taking samples, it means you just get better samples. And so if I can demonstrate that by one of the images that they give in the appendix. Let's see. So yeah, so this is the predicted corrector. So this is the reverse SDE with the score function. And then this is the corrector, which is just simply Laundromat Dynamics at a fixed time step. So it's like an inner and outer loop. And what that means is that, so here's your compute budget on the y-axis, so the total score function evaluations. And here is how many steps you pause for to correct the distribution to make sure you're sampling from a stationary distribution to make sure you converge at the current time step. So if you have 3,000 function evaluations, but you don't correct that distribution, then you've got some numerical error in discretizing the SDE, and you get quite noisy samples. But then if we correct the bias at each step, then we get better samples for the same compute budget. So for 3,000 function evaluations total, because each step of this also involves an evaluation of S theta. So it's the number of evaluations of S theta, which is really determining your compute budget. You would be better off by having 2 or 3 Laundromat steps per noise level. So 2 or 3 corrector steps and then a predictor step. And then you get less noisy samples. Yeah, there are some sort of, before I go on to the architecture and practical implementation stuff, but are there any more questions about the method?
So the corrector step, what is it? How is it correcting? Is it just, yeah, how is it correcting?
So if you go to the Laundromat Dynamics, so imagine here that we've fixed the noise level. So time is, imagine changing T to I, okay? And we fixed the noise at what we want to sample from. So we fix the time, so PT of X. And then we want to make sure the distribution X will be close to PT of X. And so we need to sample until we reach the correct area of the state space under that particular score function. And that's because the score function, it changes every time you add a bit of noise to the data. So if you're going from an image to pure noise in the intermediate steps, each time this score function changes. And each time the score function changes, you want to make sure that you've converged to the potential well. And in order to do that, you need an inner loop as well as the outer loop, because over the outer loop, these dynamics are changing continuously over time. And then over the outer loop, you freeze it in time and then make sure it's converged to those frozen dynamics. Does that make sense?
So the way I was thinking about it is that you do one function evaluation at time step t or I, and since it's a sample, it might not necessarily bring you closer to the potential well, and your corrector is choosing which one will bring you closest to the potential well at each time step.
Yeah, that's exactly what's happening.
Okay.
Choosing not so much because it's using each sample, so it's more like converging. It's because it's like a gradient ascent on that particular potential, and then you press play again on the dynamics, the potential changes, all of a sudden you're in the wrong place, and then you've got to not choose, but I say converge to the correct potential again. And so if you do flip-flop between those two inner and outer loops, then you get better samples than if you just ran the outer loop with one inner loop step.
I see.
Yeah.
That's interesting, the fact that there's different potential fields at different steps, actually.
But that's because you add noise. That's because we smooth out the potential. So if I go back to the image, need to work out how to present in something other than Adobe Acrobat. Here we go. Okay. So yeah, the score changes at each step. So that's why the potential is different at each step, because you've added noise at each step. So the potential, it might be like the circle in 2 dimensions here, but it's more like a bivariate Gaussian distribution over here in 2 dimensions. So so that's about smoothing the potential over the time, so that you can, when you sample in reverse, you can sample from the prior and explore the whole space. But yeah, you're right, because the score changes every time, then at one particular time step, you've got to pause it and make sure it arrives at the stationary distribution described by the potential well. And then unpause, move another step, and then make sure it converges.
And one just random question I'm thinking in the back of my head is how are they making sure that the sampling is a differentiable process? Is it just because it's a continuous function?
You don't need the sampling to be differentiable. In fact, it's not, because Brownian motion is not smooth, is not differentiable. It's like jagged. That's not the bit that's differentiable. The bit that's differentiable is the log density. So the log density needs to be smooth. I don't know how much of it a limitation that is. I don't know if I can think of an example where you have a log density that's not smooth. Maybe discrete distributions. So different treatment might be needed for sampling from the distribution of natural numbers like 1 to 0 to 9, because they're discrete. They're not like the color of an image is also discrete. It's a number between 0 and 255 is like the intensity of the color, but it's well approximated by a continuous number. So yeah, you just need to, you need the distribution P over that continuous space of X, the color, to be smooth. You just need to differentiate it once.
Okay, thanks.
So there are, as well as the new methodology and the predicted corrector samplers, I think there's a bit about the architecture. So I haven't gone into controllable generation. So I think this is actually the application, right? So it's like you can do you can condition on data that's known, so these pixels, and then condition on that data, you can generate new images. So these are infilling. And then there's other applications such as generating images from text data as well. I think that's called DALI, which uses this framework. And yeah, so Toby, you raised your hand.
Yeah, just there with the infilling, surely like for the areas where it's just all pitch black, do you not then lose the continuity of the score, like the gradient field? Because like where it just is pitch black, isn't that just a discontinuity there?
Basically, there's no data there, so you don't have any information. It's not that it's 0, 0, 0 in RGB. It's that you don't have a value. So conditioned on the other values, you can see that in the appendix. I think it's appendix D. So conditional. No. Industrial sampling, data corrector, training, architecture improvements. Conditional generation. So imputation is what this is called in painting, is where you have two different domains, i.e. the 0, 0, 0 RGB, which is the bar, and the 3, which is where you do the colors. And then by splitting up the score function between those dimensions of the pixels you know and the dimensions of the pixels you don't know, you can condition on the ones that you know. And somewhere in here, there's an approximation because you've got a conditional expectation on the things that you don't know, which is Z, conditioned on the things that you do know, which is sigma of X, which is the 3. And this is a conditional expectation that you can't evaluate exactly, but there's an approximation. And then that's how you sample conditionally on the stuff that you don't know from the stuff that you do know. This is what's going on here. Cool. So I was going to go over the architectural improvements as well, but in the main paper, there's not much information about that. They point you to some resources, I think, to the appendix on the specific architecture that was used, which is important because you need to be able to have the model capacity and the correct inductive biases to estimate the true score from the neural network. And so once you have those in place, then you can start to get performance that is state of the art. And then even then you would need some GPUs and probably quite a lot of GPU time to train on this high dimensional data. But the point is that it does work. Like it works for sampling high dimensional distributions that are just not possible to sample from using Laundromat Dynamics and MCMC. So the conclusion is they presented a framework for score-based generative modeling based on SDEs, and it enables a better understanding of existing approaches, new sampling algorithms. One thing we didn't cover is exact likelihood computation, which is maybe something we can go over another time. But likelihood computation is useful, I think, for a number of machine learning tasks. So this is a comment about GANs. So while our proposed sampling approach improves relative results, and enables more efficient sampling. They remain slower at sampling than GANs. I imagine that's because of the number of time steps needed in the reverse SDE. And I think I watched a video that said you only need 1 step in GANs because you train a separate discriminator and predictor neural network in GANs. So maybe that's why they are slower at sampling than GANs on the same data sets. And identifying ways of combining the stable learning of school-based generative models with fast sampling of implicit models like GANs remains an important research direction. So I think the encoded in the implicit model thing is saying that, well, you can do it in 1 time step, and it's faster to sample that way. Additionally, the breadth of samplers one can use when given access to score functions introduces a number of hyperparameters. Yeah, so these hyperparameters need to be treated by tuning over them in order to get good performance. And I'm not sure what those hyperparameters are. But if anyone knows, let me know.
Would it be the alpha coefficient in the dynamics?
What do you mean by output coefficient?
The alpha at the
like the time step of the dynamics. Yeah. So yeah, the number of time steps taken and the number of corrected. Yeah. And as well as more extensive investigation on the merits and limitations of various samplers. So I guess you could use different samplers for the corrected step. You could use different SDEs for the predictor step. In the SDE used in this paper is the Stein-Uhlenbeck, because that's the simplest possible case. And the corrector used, I think they tried different ones in the study of the hyperparameter selection. But yeah, I think really interesting paper. Because it's the empirical performance is very good and much better than what's previously been possible for sampling from high dimensional data with pretty much any realistic data distribution. So I think we can maybe finish the talk. But maybe a discussion point could be what kind of applications that generative modeling could be used for would be a good point to start with.
One quick question is, so they mentioned that GANs are faster at sampling, but for example, DALI has been mass distributed for people to try out and use. So I guess even though these methods are slower, they produce better quality samples. Is that the idea?
I'm not too sure. Does anyone know? Has anyone used GANs before?
Usually, yeah, I've seen using these models, the samples are much better than the ones that you get out of GANs. And GANs are pretty complicated anyway with sort of hyperparameter tuning and so on. So even though these are much slower at sampling, they're sort of a little bit easier and you get slightly better results than you do with GANs, from sort of what I've seen around anyway.
Okay, that makes sense. Yeah, just because I guess for me, the coolest part about this is how much it's used in practice, because it's rare that you see something that is so complex that is actually so generalizable. Usually complexity is tied to tailoring to a specific problem.
Would that be that the GANs the GANs use a distance measurement, which is, I think it's KLD. So they can tell apart the samples much faster than the diffusion models, which need sampling. The corrector phase requires sampling, which could explain why it takes longer. That's my opinion of it, anyways.
So the equivalent of KLD in this framework would be the Fisher divergence. So KLD is an integral probability metric, which means it's the difference between expectations under the model and the true distribution. And the KLD, I think, comes from KL divergence, which has been bounded so that you can use it for training. But this one is part of a larger class of discrepancies between distributions. And so what you're actually doing is you want to minimize the distance between your model and the true distribution. And in this case, the discrepancy is the Fisher divergence, which uses the score. And so that's why it's called score matching. But the difference between KL and score matching, I think, is score matching only uses local information, whereas KL uses the information about the whole distribution because it takes an expectation over the whole distribution. So that's, I think, maybe one difference.
Yeah, and like I know that the GANs, based on the entire distribution, the output is sort of like binary. So either you're close, 0, I'm talking about the discriminator, and then 1 if you're closer to the true distribution, whereas the predictor, the corrector here, takes into account the largest space. So what I mean is, because you're using diffusion model to the reverse side of it, the right hand side in the diagram, you're sort of hovering over the space, which gives you a more how would you say, view of the data distribution, as opposed to saying it's either 0 or 1, which is in GANs, which might explain why they're so difficult to train, the GANs. If that makes sense.
So what I've heard about GANs is just that they are super sensitive to hyperparameter tuning.
Oh, yeah.
So like the difference between them working and not working is usually just having massive hyperparameter searches. And so when you see, I remember seeing a talk in iClear from these guys at NVIDIA that have done some really cool things with, like, for example, doing super resolution in images with GANs. And at the very end of the talk, they were like, someone asked a question about this, and they said, yeah, and of course, we had to like train massive amounts of models to get the results that you're seeing. It's not like, which I guess is one of the hard things about GANs, in the sense that there's not like a systematic way of finding the best model. It's just a matter of having a lot of compute and searching.
Absolutely, yeah. I had some confusions with the alpha. I think it's not this paper. It's the paper Ben was describing, by the same author, with the alpha, the portion of the alpha. So if I'm correct, alpha decides how fast a sample jumps through the flow field. But also there's a portion of the alpha that decides how much the potential well is pushed because of the noise ZT. But would it be difficult to decide to tune alpha, because you could be pushing the sample within the flow field in a direction which is not close to the well? Could you have a situation where the well keeps getting further and further from the sample movement, and then you never reach that well, or is it just impossible in this case?
I think the reason why alpha appears in both terms is because it manages that trade-off automatically. So if you're having a high alpha, then your force, which moves you in a new direction, is proportional to the square root of the noise that you add. So your movement based on the drift is proportional to the square root of the movement based on your noise. So there's that link there that's stopping the noise from taking over from the drift. And there is a trade-off in picking alpha, but ideally you have alpha as small as possible. In practice, not feasible because you only have a finite number of function evaluations. So to explore the whole space of the circle, you want a trade-off. Alpha is small enough so that the numerical error of this discretization is small enough that the distribution of x will be close to p, but large enough so that you explore the whole space.
That makes a lot more sense. Cheers, Ben.
Okay, we should end here probably. We're running out of time. Thanks, Ben. Lots of great discussion. And see you all next week. Next week is in person.